As an example of algorithms in practice, let's have a look at a classic problem, Knapsack. But before we can get into the details, let's quickly make sure that we all know what we're talking about. Knapsack is one of Karp's 21 NP-hard problems from his 1972 paper, Reducibility Among Combinatorial Problems. Arguably, this is the paper that put NP-hardness on the map as a relevant concept. After a couple of pages of setup, here goes the main theorem. All of the problems on the following list are complete. Satisfiability, we know that from Cook's theorem a year earlier, and then a bunch of other problems that are all more or less famous now. Integer programming, clique, Hamilton cycles, and on the next page we get to Knapsack. We get n non-negative integers aj, and one more non-negative integer b. And we're asked the question, does any subset of them add up to b? Wait, this is not what I call Knapsack, I would call this subset sum. Let's have a look at Gary and Johnson's Computers and Intractability. They have another important list of NP-hard problems. And there it is. They call Karp's version subset sum. And their Knapsack. That's what I expected. We have a finite set of items. Each one has a positive integer size, also sometimes called the weight, and that's what we'll call it later, and a positive integer value. And in addition, we're given positive integers b and k. Is there a subset of the items such that their size is at most b, and their value is at least k? They do it like this because NP-hardness is about decision problems. We'll look at it as an optimization problem instead. Given the sizes and the values, and the size bound, we want to maximize the value. You'll see that they note that this problem can be solved in pseudo-polynomial time by dynamic programming. That's the algorithm we're going to implement, and it goes like this. We get n items with values vi and weights wi. Also, there's a weight limit big W. What is the maximum sum of values you can get, such that the sum of weights is at most big W? If necessary, pick an arbitrary order on the items, and now we'll define a function. F of I and W equals the maximum value with weight limit W, using only the items 1 up to and including item I. This is how I define f. But the trick is now that we can also come up with a recursive equation for f to solve larger instances in terms of smaller ones. Let's start with an easy case. What is the value of f of 1w? Well, we get the value of the first item, v1, but only if it fits, only if w1 is less equal w. Otherwise, we can't take the item, and the most value we can get is, well, 0. This is our base case. Now let's think of the general case. F of I and W is what? Let's consider if we should take item I. We can let the recursion figure out what to do with all of the items before. So item I, we could not take it. Then the value we get must come from the first I minus 1 items. And they can weigh the full W. We know how to do that. That's f of I minus 1 W. Okay, so what happens if we take item I? Then we get its value. That's good. And if we have any capacity left, maybe we can even get some more value from the other items. So that's f of I minus 1 again, but the remaining capacity is only W minus Wi. And watch out, this doesn't make sense if the remaining capacity is negative. In that case, you couldn't have taken the item. We could fix this by defining what negative capacity means, but let's just say we can only do this if W minus Wi is at least 0. So now how do we solve the problem? Well, given the definition of f, the answer to our problem is f of n big W, which we can actually calculate using the recurrence. So what runtime does this have? Disregarding the cost of the recursive calls, we can clearly evaluate f in constant time. The parameter I ranges from 1 to n, the parameter w ranges from 0 to big W, so we have runtime big O of n times w. This is polynomial in n and w, but watch out, this is really what's called pseudo-polynomial runtime, because technically runtimes are for Turing machines as a function of the input size. Big W is part of the input, and I could write it in binary, so in a certain amount of input size, I could actually describe an exponentially large value of big W. Then n times W is exponential in the input size. But it does mean that if our weight limit happens to be small, in practice, then we actually have a really efficient algorithm. Let's implement it and see how that goes. Let's turn this theory into practice. We'll take it easy and start in Python. Here, I've started typing a little example instance. We have the weights, the values in these two lists. Let n be the number of items, and we'll say big W, the size of the knapsack, is 30. We're going to need to do dynamic programming. That's what gives us the runtime bound of order n times W. So it's not entirely this simple, but just to be sure, let's start out with a recursive implementation and take it from there. So we have this function f with parameters I, an item, and W, a weight bound. First of all, if the weight is less than 0, then clearly this isn't going to work. I could check this whenever I call f, but then I need to do that, and I'm not sure that's going to be much fun, so let's just do it here. If w is less than 0, we return minus infinity. Next, we'll do the base case of the recursion. If I equals 0, that is, if we are considering only the first object, then we get its value. Well, only if it fits, of course. Otherwise, we get nothing. And then we'll just do the recursive case, just like we talked about with the recurrence relation. We return the maximum of f I minus 1 w. That means we don't take item I. So we get the same as with only the first I minus 1 items. And f I minus 1 w minus the weight of object I, plus the value of I. That's it. Working program. Well, actually, no, we still need to call this. Let's actually print n and w and then time how long it takes to call f of n minus 1, because these lists are 0 indexed, and w. Okay, run it once. Let's see. This is taking a while. Nine seconds. For 32 items. I mean, this problem is NP hard, so maybe? But no, this program is just bad. We just did this to see how bad. This recursion is out of control. Every call makes 2 more calls. Well, not quite. If the weight parameter goes out of bounds, that stops it too. So with a really small weight limit, maybe this is fine, but crucially, this is not actually an implementation of the algorithm I talked about. This doesn't do dynamic program, and its runtime is not bounded by O of n times W. Let's fix that. The crucial idea of dynamic programming is that you only ever evaluate the function once for any particular valuation of the parameters. But how do we implement that? Here's an idea. Let's just make a dictionary. Hash map if you want, but basically any data structure where you can store key value pairs. And before we actually evaluate the function, we check to see whether we've done that before, and if so, we return that. Otherwise, we evaluate the function for real, and before we return the result, store it in a dictionary. This is called memoisation, not memorization, memoisation. And as you can see, this is a higher order function. You can memoise any pure function, that is, any function without side effects whose result is uniquely determined by its parameters. A function in a mathematical sense. Python has higher order functions. Let's see what happens. I'm not going to go into the implementation of this Memoise2 function here, too much Python stuff, but it memoises a binary function, a function with 2 arguments. We make a new function that has a dictionary, and if we get 2 arguments, we first check the dictionary and then call the original function if necessary. I actually found out after I recorded the video that Python has a built-in library for memoization. It's called Cached, and it's in the functools package. It might perform a bit better than what I've kludged together here, but at least now you can see what the idea is. So now we say that f is memoized, and that's the only change we're making to the actual program. In a sense, we are now done. We have achieved the asymptotic runtime we wanted, O of n times W. We can go home now. I'm assuming here that the dictionary operations run in amortized constant time, which is actually its own can of worms, but I don't really want to go into that now. So we're done. Well, I have a sneaking suspicion we can get it to go a bit faster still, but I wanted to point out that from this point on, we are in the game of constant factors, not big O improvements. So let's check out how we're doing. Well, okay, that's faster. More than 5,000 times as fast. But on the other hand, the instance is tiny, let's be real here. We need something bigger to chew on. This is an instance with 200 items, maximum weight 9,000, and it took almost 3 seconds. Now the game is on. How much faster can we make this? Let's actually start putting these results in a table. Here it is. A small and a medium instance with a recursive implementation and the one where we use the decorator to memoise the recursion. As the next step, let's throw this decorator out and do it by hand. This is partly to show you what it looks like in a language that doesn't do decorators like this, but also because we were memoizing the calls with -w. We don't need to do that, since those are actually quicker to evaluate than to look up, and the dictionary will stay a little smaller. So let's get rid of the decorator and instead make our own dictionary. Let's clean this up a little bit, and after that we check the dictionary. If the answer is in there, we just return it. Otherwise, let's clean up the base case real quick, put it over here. And now we don't want to just return the function value, we put it in the dictionary and then return it. Actually, let's also output the result. This last line, line 28, is basically free. We call f n-1w a second time, but the answer will already be in the dictionary. So is this any faster? Yes, by a bit. Let's put it in the table. Now me personally, I always get a bit uncomfortable around hash maps. They're often super useful and easy to work with, and in the right place they can be highly performant. But whether they are fast in any particular use case is decidedly non-trivial. Performance can depend on a lot of things, and again, I don't really want to talk about hash maps, it gets very complicated. But let me say this, if you have a good way to directly address the data without needing to do hashing in a way that is convenient for your machine, there's the potential to do much better. And we do have a really convenient way to address our dictionary. We can just put it in a 2D table, indexed by I and W. So let's get rid of this dictionary and instead make a list of lists. And we'll initialize the values with -infinity so we know if we've stored anything there. Then we can check for -infinity here, update in other places, and go. Aha! Almost twice as fast. This is just anecdotal, of course, but I think you'll agree that the dictionary wasn't free. Those are some decent improvements. I'm feeling lucky. Let's try a larger instance. Ha! Okay, I see what happened here. This instance has almost 5,000 items, and our recursion overflows in the call stack. A lot of the time, we will just get our answer from the table, but in order to reach a base case, at some point, we're n deep in the recursion. That's not really a fundamental problem. Python could have a larger stack if it wanted. This is not an unreasonable amount of memory or something like that. This is just the way it's set up. But instead of trying to see if I can somehow increase the stack space, I'll take this as an excuse to move to a different implementation strategy. We'll make the table just like before, but this time we'll go through it systematically. This is often how you'll want to implement a dynamic program. It's even often how I think about a dynamic program, though theoretically there is nothing wrong with what we've done up until now. So the observation is this: the recurrence for f of I and w only ever looks at smaller values of I and w. So we can go through the table in order of increasing I and w, and the things we'll need will always be available already. We can actually just pick in which direction we do this, I first or w first. But we have this base case for I equals 0, so let's start there. I've initialized the table with zeros this time, so the only thing to do here is to set the values in the first column to the value of the first item. Well, if w is large enough. First column done. Now for all other columns, for all increasing values of w, and watch out, we run up to including big W, we look at the two cases. Don't take the item to get the same as before, or we take it, if we can, to get extra value. Put it in the table and return it. Moment of truth. Is this any faster? Yes, not dramatically faster, but it's faster. Now, let's try the big instance. Okay, right. This is taking a while. You've seen all the programs in real time until now, but I'll cut here. Welcome back. This is 85 seconds later. That's not great, but we couldn't even do this instance before. It crashed. So it's some kind of success anyway. Let's put it in the table. I don't want to unfairly malign Python. It has lots of things going for it, and I don't know so much about writing performant Python code. There's a couple more things we could do here, but let's actually switch language. Here's Java. This is not super exciting. It's basically the same idea as our last version in Python. It's just a bit more verbose. We have an item class that just carries our values around, some stuff to parse the input. This is our dynamic programming table as a two-dimensional array. Well, actually as an array of arrays, but we'll get to that. And the rest is just the same as before. The base case, Java arrays are initialized to 0 also, and the recurrent case. The stuff here is structured a bit differently than in Python, but it's basically the same. The result is over here. Let's compile it and run it on the medium instance. Okay, that is a big difference. We're back down to fractions of a second. Time for the large instance. And this, okay, only half a second. Well, it's less than a minute and a half. But maybe there's more we can do. Now here's something I'd like you to think about for a second. What happens if we flip this? What if we put the table the other way around? I'll actually let you think about this for a moment. Maybe you should pause the video. Actually think about this. Why would that matter? And if so, which version is better? The old one or the other way around? I'll wait. 3, 2, 1. Okay. Welcome back. Do you have your answer? Let's see. Oh, this is much slower. It runs for almost 4 times as long, but why? Well, let's think about what this line means. This is the first version I'm showing you here, the fast one. What does this look like in memory? We have an array, so that's really just a pointer to a block of memory somewhere. What's in that block of memory? The values of the array. But that's more arrays. So really it's more pointers to more blocks of memory somewhere. That's where the actual values are. So if we look at this access here, how does that work? What does the computer end up doing? How do we get this value? So if this value table, right, it's a pointer. We follow that pointer plus I minus 1. That's where we will find the right column of the table. Maybe Java will also do a bounce check here to see if we're staying inside the array, but let's not worry about that for now. What we find there, it's the pointer to the right column, so we have to follow that pointer plus W. That's where the actual value is. This was actually quite a faff to get to this value, and here's something to think about. We will only know the second pointer after the result from the first pointer comes back from memory. We'll only know where to go after we've waited for memory once. Well, I guess we'll have a pretty good chance that the first pointer will be in a cache somewhere, since that first array is pretty small and we look at it all the time. But I digress. How does our program go through this table? First, it goes through the entire array table 0. Then it goes through the entire array's table of I, one at a time, because I is the outer loop, and I is the first index in our nested array. For visual simplicity, let's not track all memory accesses, but just look at the order that the main for loops go through the items. This is the first version, but now let's do it the other way around. Doing it like this is a disaster for memory locality. That means, does your program access locations that are generally close to each other? We don't really have time to go into much of why memory locality is good, but one of the reasons is caching. And caching doesn't happen on a byte level, so a cache might even have things you didn't look at yet, if it's just near something that you did. We'll talk about this a little bit more later, but the main takeaway here is that stuff like this matters for performance. Memory layout matters. I mean, I don't know if you care about a factor 4, but these kinds of things can add up, and at least this one, I could have told you in advance. That's why I wrote the good version to begin with. Just pause a second to think which axis is the outer loop and therefore which axis should be the outer array based on how I access this table. So here are the runtimes. I think we can do better than this, and just like we could have done at least a little bit better in Python, we can definitely still do better in Java, but let's move on to C++. Here's the basic version. Same idea, a class for items, the base case, and now we do need to set all the zeros by hand because C++ doesn't do that for us by default, and the for loops. Here we also have the nested arrays, the right way around again. And in preparation for playing with the recurrence a little bit later, we don't just look at the table n-1w at the end, but we check the entire last column to see where the highest value is. That's not really an optimization, that's just a slightly different way of doing things. Don't worry about it. So how fast is this? It is actually faster than pretty much the same Java code, but not by a lot. Just for fun, let's also try doing the table the wrong way around again. Are we affected by that? Yes, it's a pretty similar effect. I don't know what you expected, but C++ and Java are actually pretty close here, and that doesn't surprise me. If you're just crunching numbers, and garbage collection is pretty easy in our program, for example, there's just not a lot to choose between them. But let's see if we can go faster still. Now, I already complained before that we have to go through 2 pointers to get to any entry in the table. Let's flatten it into one block of memory. And because we want to go through the columns efficiently, we'll do it in so-called column major order. We'll put the value in column I and row W at the following index. W plus I times the height of the table. That way nothing overlaps and everything is contiguous in memory. And if we go through a column, that is all next to each other in memory. So in order to implement this, we'll have an index function, a one-dimensional array. So that's also good for locality because all of this memory is together in one block. And we get the values through this index function. And indeed, it is faster. Not a lot faster, but these runtimes are pretty small anyway. Let's keep going. We spent quite some time doing basically the same thing, but faster. Let's make an observation that's a bit more algorithmic in nature, though really we're still kind of just doing equivalent things. The observation is this. We don't really need more than 2 columns of the table at a time. The recurrence fiw equals such and so only mentions the column I-1. We'll never need column I-2 anymore. We've already used that information. I should point out here that this isn't a C++ thing. We could have done this in Java. We could have even done this all the way back in Python, and it would have helped. But we're just exploring this together. We're not trying to rank programming languages. Now we have only 2 columns. Let's call them fold and fnew. That's really going to be f of I-1 and fi respectively, the previous column and the one we're working on now. Base case, fill fnew with zeros and put the value of item 0 precisely at its weight. Don't worry about it, it's just something I was playing around with and it didn't go anywhere. I just didn't want you to wonder what's going on here. But more importantly, our main nested loops are now this. Step 1 is flip fold and fnew. We don't swap the values in the array here, of course, we swap the pointers, so this is basically free. This allows us to have the same code for the even and the odd columns. And then we just replace all of the lookups with fold and fnew, and that's it. Oh, this is actually almost twice as fast. Look at how far we've come. This could be a decent point to stop, but let's do this one more thing. I think it's pretty fun. We'll stay with the 2 arrays for the 2 columns, but here's small trick number 1. Instead of writing a for loop ourselves to initialize the column, we use a function called memset. Do you have a block of memory that needs a particular value all over it? You call memset. It's supposed to be a heavily optimized function, optimized for your machine using whatever fancy instructions your processor has. It's supposed to be the optimal, the actual fastest way to fill memory with a certain value. You have the overhead of calling the function, but other than that, you're going to win. And this is why I wanted to write only one more value into this array. Setting it all to 0 is so fast. That's just the first column, so it's probably not really significant, and we can't really expect there to be a function like mem_knapsack in the standard library. But there is a function called mem_copy. You give it pointers to 2 blocks of memory, they're not allowed to overlap, and it copies the values from one into the other. This function moves bytes as fast as possible. Okay, sure, but why do we need this? Well, the comment kind of gives the trick away. Up until now, we've gone through the column once, and at each cell consider 2 options, take or don't take. That is fi-1w or fi-1w minus weight I, if that weight is in bounds. Now here's the thing. That first term, fi-1w, the don't take option that we always have, that's really just copying the entire previous column. Then sometimes we take a different option, but let's think about that later and start out with the copy. After that's done, we go through the entire column again. That sounds like more work actually, but we have some things going for us. The second pass through the column is easier than our old pass. What we used to do was look at two things, take and don't take, and for one of them we needed to check if it's in bounds, and if it is, then we put the larger of the two into a third place. The mem copy has taken care of all of the don't take options, so now we don't have to. All we do is check if we should instead have taken the take option. There's a bit of pointer juggling going on here that's not super interesting. Maybe for fun you can try to figure out how it works, but that's not really important. The real question is this faster? We go through each column twice now. That sounds bad, but both passes are simpler than the original one. Memcopy is going to be super fast. And our take pass is also somewhat simpler. It looks at fewer memory locations, for example, and the math with the offsets is a little bit simpler, so, well, I don't know. We'll have to see. And we have a winner by quite a bit again. You know what? We've fought ourselves back down to a fraction of a second, but what fun is that? Give me a bigger instance. This one has 1,000,000 items and a weight limit of 10,000. Okay, this hurts a bit. And 8 seconds. Well, I'm going to say not bad for 1,000,000 items. We started out with 9 seconds for 32 items. Okay, that's not fair. That really wasn't the correct algorithm. But on the large instance, we've improved by a factor of about 700 over our first implementation that I would call decent, the dynamic programming table in Python. This 700 is a constant, but I'll take it. Surely we could have made that one a bunch faster still, and it shouldn't count for nothing that we did have to think quite a bit harder this time and type quite a bit more to get these faster versions. But I do maintain that this final C++ version isn't that insane. It's pretty readable. I would be remiss if I didn't mention one more aspect of algorithms in practice, and that's using off-the-shelf modeling tools and so-called solvers. We really don't have time to go into details here, or even give a decent overview, but let's have a quick look at integer linear programming. That's actually one of Carp's complete problems, and it's a really convenient one for describing other problems. There are also a bunch of commercial solver packages that are really good and make it even easier to use. And some of them are free for academic use, like this one, IBM's Cplex. Like I said, no details, but let's just try to do Knapsack real quick. This is some weird little modeling language. Don't worry about it. We'll have some values and some weights, a tiny little test instance, and a maximum weight. These are normal variables. Well, they're constants actually, but now we'll make a dvar. It stands for decision variable, I think, and we don't have to say what value it gets. The solver will figure this out for us. Let's have it decide, for each item, do we pick it? So now what? What should it pick? We can just tell it that we want it to maximize the value of the items that it picks, the sum of pick I times value I. We can't just write whatever here. It has to be linear in the decision variables, but don't worry about it. That's a whole different lecture. We're just having a quick look. This actually still is really easy. It can just pick everything, get all the value. This isn't Knapsack. But we can just say, subject to weight of the picked items is at most max weight. Boom. Done. We are allowed to write this. Let's run it. So it has apparently figured out, pick the second and third item, get value 10. That's correct. Even if it's not very impressive at this point, but let's get a bigger instance. We'll do the large one from before. It has 4,900 items, and I've put the weights and values in a different file. Syntax for that is pretty funny, I think. And that's it. Let's run it. Oh, wow. Okay. It finds the solution in 0.6 seconds. That's really fast. It's almost as fast as our initial Java and C++ code. It found a solution and wait a minute. That's not what we got from the dynamic program. At this point, I spent 2 hours trying to find the bug in the dynamic program, but... aha. It says integer optimal, yeah, but tolerance. It has found a solution with value 87,194. And it has been able to prove that the optimum cannot be more than a certain tolerance factor above that. But what is this tolerance factor? Okay, I see. It's 10 to the minus 4. Well, thanks for that. That's 2 hours of my life I'm never getting back, but I do these things so that you don't have to. If you use tools, try to know how they work, at least to some extent, so that you don't shoot yourself in the foot like this. And I'm not even saying that this default is bad. It's probably the default for a reason, and in practice, an approximation factor of 1.001 is probably pretty good. But me, I would like an optimal solution now, thank you very much. So let's set the tolerance to 10 to the minus 7, that should do it. Run it again, and pretty much the same runtime, actually. Did we get it? We got it, 96. That is impressive. But let's see if it can keep up. Let's bring out the huge instance. Okay, it's launching, whatever that means. We're 9 seconds in now. Our C++ code was already done at this point. Something called pre-solve. It's even multi-threaded, it looks like, which we aren't. That's something we've ignored completely. Whether it would help the DP is an interesting question that I'll leave open, or how you would solve Knapsack efficiently in a multi-threaded setting. There it is. 32 seconds. Well, it spent 32 seconds on branch and cut, but including model building and that pre-solve and everything, it was actually 52 seconds. So at least on this instance, our specific algorithm and our specific programming effort were able to give us the win, significantly. Part of that is that I picked maximum weights that are reasonable for the DP. I haven't tried, but it's likely that the LP solver will win on some other instances. If you make it so that the table is too large for main memory, for example, the DP is screwed. And that's what keeps it interesting. Performance in practice is a fractal of complication and subtleties, all the way from algorithmic considerations down to hardware behavior. It can be frustrating sometimes, and it can be hard to wrap your head around everything, but it rewards effort and experience. You can make it faster if you try, I promise. Well, except memcopy.